And our next speaker is Professor Greg Dierlein. He is the John Bloom Professor in Civil Environmental Engineering at Stanford University. He is co-director of the NSF-supported Computational Modeling and Simulation Center for Natural Hazards, the so-called SIM Center, and director of the John A. Bloom Earthquake Engineering Center. His research focuses on performance-based earthquake engineering of buildings and civil infrastructure, with emphasis on nonlinear analysis, design, and behavior of structures. Greg, welcome. It's great. I really look forward to your talk. So the floor is yours.
All right. Well, great. Thank you for that introduction, Sharif, and thank you to you and your colleagues for putting on this seminar, the workshop today. So as Sharif mentioned, I'd like to share with you some developments that my colleagues and I at the SIM Center have been doing. And just to state at the outset, this is a contribution of many folks to work of whom I'm presenting here, along with some related projects that use some of these kind of workflow tools that I'll describe. So the SIM Center is one of several centers supported by NSF under the NEARI mission. Unlike some of the other centers, which are lab facilities, our goal is our task is to develop software to support natural hazards engineering across a whole range of hazards. Our kind of strategy to this, recognizing the multitude of hazards we're looking at and spectrum of resolution, is not to develop one tool, but to develop computational workflow applications that are flexible, extensible, and scalable, and also that recognize that we need to do a lot of computations to characterize uncertainties in natural hazards engineering. So it's developing those frameworks. The next thing is to seed the framework with enough data and interfaces to some existing simulation tools so we could start to apply these and engage other researchers in using them and adding to the tools. We're building some applications on top of these workflows to facilitate their use. And finally, the last thing is kind of building an ecosystem. All of the tools I'll describe are available in open source. If you go to the SIM Center webpage, there's documentation continually getting better, webinars to describe the tools, forums to exchange ideas, because it's really going to be the whole community ultimately contributing and using these tools that makes them work. The workflow I'll describe is kind of based in part, large part on a performance-based engineering framework, which some folks from earthquake engineering may be familiar with, but thinking carefully about the facilities we're looking at, characterizing them, the hazards they're subjected to, going through structural analysis, damage, loss analysis, and finally feeding into decision-making, and thinking very carefully about the different modules here and how data flows from one component of the analysis into the other. So with that underlying concept, our application framework for the workflow is described by these puzzle pieces. You can imagine each puzzle piece is kind of one or more models to simulate some aspect of the response that's encapsulated in some pre and post processors that connect it to this chain of passing data from one segment to the next, also into external data. So if you look from the left side, it starts at describing assets and hazards, going through the damage and response to simulating recovery. It's connected to supporting databases on describing hazard effects, describing inventories, and also to tools that can help with characterizing uncertainty. And so the idea is it's an open source framework, multi-fidelity, multi-hazard, where you can plug and play different modules. So from that puzzle piece that we've then derived, and this is kind of the brainchild of Frank McKenna, who some people may know was the kind of architect of the OpenSeas framework for simulation, but an object-oriented framework where we have a number of components shown across the bottom that are basically the realizations of those puzzle pieces. Up the right-hand side, they're connected to databases of inventory, hazard effects, and so forth. And then built on top of that are some of these workflow applications that I'll describe. Now, all of the tools that I'm describing on this slide are part of a bigger ecosystem within the NEARI framework. Our tools are shown in, say, the center of the graphic here. On the right side are the supporting technology infrastructure provided through DesignSafe. That's another center, part of the NEARI supported by NSF, that has both large data storage, but also has high-performance computing through the Texas Advanced Computing Center. So our workflow applications are running on that. And on the left side of the slide, being able to tap into online cloud resources. Could be facilities from USGS, could be inventories of buildings from tax assessor databases and so forth. And really through this, then the user has access to running these tools and then can output the data into their own user application, say for visualization or further manipulation. Now, I won't describe all of those workflow components, but I'll mention a couple. On the front end, that is describing the assets or the building inventories or inventories of other facilities, of course, there's databases, tax assessor databases, building departments, but we've also been exploring using some AI techniques, in particular image recognition for both satellite and street view images to further describe aspects of the assets, and also developing some tools to fill in gaps, again, using some AI techniques to kind of make inferences to fill in gaps in that database. So that's a set of tools that we've been trying to push forward as well on the front end. Looking at the assessment of damage to facilities, we built up a library called Pelican, Probabilistic Estimation of Losses, Injuries, Community Resilience Under Natural Disasters. But basically it's an inventory or it's a library of features that we could, or tools and data sets that we could describe the damage to facilities. We've been starting in kind of the earthquake realm, but then building that out to include hurricane, storm surge, and wind effects, and then going beyond buildings to also look at infrastructure systems. Now, the idea with this tool is that it's kind of multi-hazard, but also it's multi-fidelity. By that, what we mean is that if you think in the earthquake arena, we have things like hazardous functions that are kind of broad brush that come in and given the intensity of ground motion, make direct predictions of damage, to things like FEMA P58 and assembly-based method. So shown in the graphic on the right is just an illustration that there's multiple paths by which you could evaluate damage, some of which going from intensity direct to vulnerability functions to the decision variables, and others taking the approach that are going more through detailed structural analysis, response simulation, component-based damage, and assembling these. So the idea in this Pelican library is to allow for a variety of ways of different resolution and techniques that one can use for assessing the damage to individual facilities. I mentioned that on top of these kind of workflow tools, we have a number of workflow applications. One of them called QuoFem here, that's kind of coupling tools for quantifying uncertainty, statistics, reliability methods with computational finite element methods to say do propagation of uncertainties, optimization or calibration of material parameters, and eventually developing, say, surrogate models. The middle layer here would be taking these sort of detailed tools and building them into earthquake engineering, wind engineering, and hydro. That's looking at storm surge and tsunami inundation, but that is coupling these detailed models and uncertainty quantification with the corresponding hazard effects. Next, that could feed into a performance-based engineering tool, which takes the response simulation and brings it through that Pelican library I just described to describe the damage. And then finally, there could be a tool for chaining this all together into regional simulations. Next, I'd like to talk about a few illustrative applications that we've put together. The first is looking at a simulation of an earthquake effect in the San Francisco Bay Area. For this one, we're using an ensemble, actually, of simulated earthquakes that came from the Lawrence Livermore National Lab Group, simulating this earthquake. We've collected from an inventory of 1.84 million buildings from various data sources, and then using tools. In fact, Xingzhen Liu, who spoke earlier today, we're using one of his tools to make inferences between the database and our OpenSeas model. So we're doing OpenSeas simulations of the 1.84 million buildings under 25 pairs of ground motions, and then assessing damage to each of these. So part of this test bed was put in place to kind of exercise the workflow, but also to purposely ramp it up, to scale it up. And as you see on the bottom of the slide here, tapping into high performance computing resources, this took 16 hours on, say, 13,000 cores of computing to run. We don't have time to go through all the results of that, but the scenario we looked at here was one that was actually also done as part of a USGS Haywire scenario, some of you might be familiar with. And we have some comparisons that are shown in the lower left of the slide between what came out of the Hayward simulations and what we got out of ours. There's a number of reasons we could look for differences between those two. But what I really want to focus on here is a distinguishing feature between the tools we're putting out is really the high resolution, being able to take these down to parcel level, building level simulations, as opposed to kind of census block. And I'll talk a little bit later on how we could, once we could get down to that parcel level, we could start to use these simulations to engineer structures in ways, or engineer cities in ways that we couldn't before. A couple other test beds. One is taking those same sort of tools and looking at a hurricane test bed. We chose Atlantic City for this, which has an interesting mix of buildings, and of course it was inundated by Hurricane Sandy and is at risk for other hurricanes on the East Coast. You know, here we have about 20,000 individual building parcels in Atlantic City and a few of the surrounding townships. We have models that we've brought in for characterizing wind effects and also storm surge. And in the test bed we're looking at here, 25 storm tracks that say represent a Category 5 hurricane coming ashore at the location shown. And then here, now this is an area where we didn't have as much background, say, as on the earthquake on detailed structural models, but we've used models, some of the models and rule sets from HAZUS. And this is where we also enhanced our database using some of the AI tools I mentioned, for example, looking at satellite images to infer roof shapes, which are important for some of the kind of HAZUS damage functions that were evaluated through the Pelican software. And finally, the last test bed I'll mention that we applied the workflow is looking at water systems. And again, this was to really branch out beyond buildings. One of the tricky things here is coming up with the data sets that we need. In this case, we used Memphis has been looked at by a number of kind of earthquake centers over the years. So we took that data set, and here we were going for kind of a higher resolution representation of the pipeline network, where we could look at not only breaks that would interrupt a link in the network, but also to think about the breaks, how long it would take to repair things, and then feeding that into a Bayesian approach, Iris Tien at Georgia Tech looking at network modeling from this data. Okay. Now I have two other things I wanted to show. I'm watching my time, and I'm going to skip this first one. Sorry about that. And I'm going to talk about a second study. This is kind of a parallel thing to kind of a research study, not done by the Sim Center directly, but kind of using some of the tools and ideas. This was motivated by several things. One is a tall building study that was done in San Francisco, asking the question about the concentration of tall buildings in its downtown, kind of understanding the inventory of building and what risks they might propose, given that it's a mix of older and newer buildings. But also, folks might be familiar with the San Francisco Resilient City Project, which about 10 years ago came up for some concepts that have since made their way into the NIST community resilience planning. And in this graphic on the right, just showing, looking at community functions, and the idea of these frameworks is for the community to think about, after a characteristic earthquake, how quickly does the city want to recover office space, retail spaces, and so forth, and then looking at the reality of what they think the current inventory can provide. So this little study I'll show is one looking specifically at offices and the interaction of office space and recovery with tall buildings. This was done by a student at Stanford, Ann Hulsley, who just kind of completed her PhD on this. But in particular with tall buildings, we were looking at the question of if there's damage to a tall building, it's not only the recovery of the tall building itself, but if there are cordons set up, that is, if there's a danger to neighboring buildings, that could impede the recovery of neighboring buildings, emergency response, and so forth. So that was kind of a focus of using some of these workflow tools to kind of explore this question of building cordons. You know, so briefly glossing over some of the details here, looking at simulations of tall buildings and the damage that occurs to them, and then thinking of, based on that damage, would it be enough damage to trigger a cordon around the building, and then to look at what would be the time required to stabilize the building, to take away the cordon, and then to finally bring that building back to functional recovery. And so you could go through a detailed analysis using some of the tools I described for ground shaking of different intensities, and say for any one of those buildings, develop some statistics on the repair time for the building or stabilization time. And so the idea is you could do this for a number of the tall buildings, kind of bring those in and then look at an earthquake scenario to see the cumulative effect of damage to buildings in the community. And then the next thing with the cordons is from any one tall building to then look around if there's a potential cordon around that, which the guidelines are something on the order of the height or 1.5 times the height of the building, to think about not just the impact on the building itself, but on some of the neighboring buildings. So thinking about the neighboring buildings in downtown for recovery, there's a tool or a set of models out there called READY, which are looking at the recovery of buildings, which start with looking at repair time, but also interject impeding factors, that is mobilization of engineering and contractors, finances to bring a building back online. So in this project, for example, we could introduce cordons as another impeding factor. So if your building recovery is affected by damage to a tall building nearby to you, that's going to be another impeding factor that we can bring into this. So if you think about the recovery time that's kind of shown graphically here, blue would be the ordinary impeding factors that a building would have. Orange would be the additional impeding factors brought on by the cordon. And finally, once the cordons are out, then there's repair. So you could imagine if you go through time that depending on the building, some buildings might be affected by a cordon, and as you march through time, the cordon is lifted, and then you could get on to the repairs of the building. So with these workflows for communities looking at multiple buildings, you could look at under the scenario earthquake damage to tall buildings, damage to the surrounding buildings, and these two kind of map graphics in the lower picture here. First one shows 4 months after the earthquake, and you see a lot of blue there. A lot of the buildings are just affected by their own impeding factors. There's some orange there. Those are buildings that are impeded by cordons of nearby tall buildings. If you go to 12 months after the earthquake, modeling sort of the reconstruction, you could see that many of the buildings in the surrounding neighborhoods are back online. They've been repaired, but there are some that from these tall buildings might be still waiting for the lifting of the cordon to get the repairs underway. So this is the kind of micro, if you will, engineering of a city that we could start to do with these tools. And we could quantify these effects. Again, I won't go into the details here, but if you look at, this is a plot in the lower left looking at the recovery of office space in terms of percentage of office space that's there in the city days after the earthquake. We could do multiple simulations, taking in different sets of ground motions, characterizing the uncertainty of that, and say getting some expected values. And that will be a recovery curve over time. We've seen these resilience curves many times, but here we're going to deaggregate it into, for that recovery of office space, how much is due to repair time, how much is due to the impeding factors, and how much is due to the additional impeding factor due to the cordons. One can also then look at other ways to characterize it, is to think days after an earthquake, going back to the resilience guide to say, what's going to be the probability that you can recover, say, 50% of offices after an earthquake? And so you could look at after 4 months, or you could look at after 12 months, and seeing if you want to get that 50% recovery, what's the probability or the chance that you can get that recovery to happen? So then we could take this sort of information and start to look at decision making. How do you kind of mitigate these risks? So there's kind of a benchmark we have by looking at the initial data, but then you could look at different mitigation policies. You could look at looking at the extent of cordons, how big the cordon needs to be, and then you could look at ways to shorten various impeding factors. And Ann Holsey looked at these as part of her study. I won't kind of mention those all of them here, but just to point out, you could imagine if you have contractors on contract to say go in and stabilize tall buildings right after earthquake, you cut down that impeding factor, and that can have some benefit. Another thing that's often discussed is, do you need to retrofit some of the older steel moment frame buildings to protect not just the building but the neighborhood? And so you could explore those kind of options that could decrease the number of cordons that would be triggered, number one, by retrofitting those buildings and seeing how that can influence the recovery of the whole city. So we think these sort of tools are important to then kind of engineer policies. And then one can look at the probabilities of recovering functionality with these different mitigation steps. So 2 more slides, Sharif, and I'll get through. And I think the important thing to recognize here is that these are giving us tools to design the future. This is a plot of, say, looking at the effect that urban growth is always going to increase risk in cities, even as well as we design buildings and infrastructure. Just by the fact we have more people, more buildings, that's increasing risk. And it's hard to change that curve, but you could think, what can we do today through policies, through mitigation, retrofit, and others that'll take some time to implement as new buildings are brought online or as buildings are retrofitted to project out into the future. So I think what's exciting about this kind of framework we've described here, especially the open source part of it, is that you can really connect in different kinds of models. At the left end, you could imagine putting urban planning, urban growth models, and looking at policy interventions to think how the assets in a city, the buildings, can evolve over time, and you could evaluate it. And then on the far right, looking at kind of recovery modeling and socioeconomic implications. You could look at sustainability, ecological impacts, and so forth of natural hazard damage. So I think I'll wrap it up there, and hopefully there'll be time for questions. Thank you for your attention.
Thank you very much, Greg. It's exciting to see the advances that SimCenter is making. And I have a number of questions here, so I'm going to read them out. There's one from Dr. Terry McAllister. She's saying, Greg, thank you for your presentation and highlighting the SPUR example. What are some of the challenges the SimCenter is facing in addressing, SimCenter is addressing in modeling recovery? What are some of the challenges the SimCenter is addressing in modeling recovery? So,
yeah. Well, thank you, Terry. That's a great question. Well, I think, as I mentioned at the outset, that the SimCenter, we're putting together these workflow tools, and we're not charged with doing the research to develop the models that go into this or the data sets. We've done a little bit of that to seed to demonstrate things work. So one biggest challenge is getting the community energized to contribute the tools and to this. And in terms of recovery modeling, actually, we had a workshop last January where we kind of looked at that. A number of important issues, one of the key ones of which is the different data sources that one needs to model recovery. You can imagine having agent-based models to simulate recovery processes that might look at the availability of resources and finances. But I think kind of being able to identify all the data sets you need and bring coherence to it with metadata and so forth, that's one of the big challenges.
Indeed. There's another question from Omar Siddiq. He says, thank you, Professor Greg, for the interesting talk. I have a question about the cordons around the tall buildings. Do they take into account the collapse of the buildings or just the damage prior to collapse?
Well, the whole idea of the cordon, well, it takes into account damage in the sense that you could simulate a building under an earthquake, and the amount of ground shaking you have, there'll be increasing damage. I mean, at certain levels, there might be damage to the building, residual drift, that you can assess that the building poses extraordinary risk to, say, collapse in a future aftershock, and that's what would trigger a cordon. Of course, if the building gets heavily damaged and collapses during the earthquake itself, then the cordon question is moot. But there's a number of kind of interesting and challenging issues to characterize damage to building, and if you will, it's post-earthquake safety, which is kind of a key issue for establishing a cordon.
So the next question is from Puria Kurepaz. Thank you for the great presentation, Professor Dearline. Can you please elaborate on the application of AI methods in your studies? Did you use these techniques to generate exposure models for seismic risk assessment?
Well, the most place we've so far used the AI where we found it works pretty well is actually in the hurricane testbed, where external features of the building, particularly roof shapes, was something that the image classification techniques were very well suited to. Another one related to that is for storm surge, identifying the first occupied level of a building. That's something that we can infer pretty well from visual imagery. We've also explored applications to seismic, looking at soft stories, and we have some work there, but I think one of the challenges is to really, you're limited by what you can infer about a building from visual images from the outside. So some hazard effects are more amenable to that than others.
There's a question from Yvonne Pena. She is asking, did the study consider any simplification of buildings with seismic protection systems?
Short answer is no. And that's again because some of these studies each study has a focus. Some of the things the Sim Center did, that early test that I showed, is really to demonstrate the tools. We don't have the resources to build out the inventory to identify seismic protection on individual buildings. But again, our hope is that the framework is flexible enough where one can do high fidelity modeling of certain buildings that say have protective systems, seismic isolation, and say, look at the effects. One could say, for example, if you had seismic isolation on emergency facilities or on power facilities, how could that affect the resilience of a community? So we didn't do that, but we think the workflow we have can support that sort of thing.
The next question is from Mohsen Zakir Estoremati. He is asking, did you use similar 2D plastic hinge models as the tall buildings you showed in your city scale analysis? If yes, does the Sim Center workflow provide such OpenSea structural models to be simulated for hazard scenarios?
Yeah, well, for the San Francisco, the 1.8 million buildings, those were OpenSea's models, but they were story-based shear models. So you didn't get down to the hinge level. But the idea is that if you look at the Corden problems, that you could model, say, a few tall buildings with more detailed hinge-type models. Now, the Sim Center tools, again, they embody kind of OpenSea's in the data chain. And all of the studies that we showed here, well, the Sim Center studies that I showed of, say, San Francisco, will be publishing those data sets, and that'll be available on GitHub that you can look at. So those are available. But our really hope and the mission of the NERI is that the whole community, and through Design Safe and the Data Depot, as people do these studies, they all contribute their computational models, much like they would experimental data, and really leverage all the assets of the community. So for instance, if a researcher is interested in simulating recovery, they don't have to recreate this whole scenario. They could use the data and the models that other people have done, and then they could just focus on the simulating recovery. Other people might want to look at protective systems of buildings. They could plug in their modules to that part.
We have a question from Laxman Dehal. He is asking, do these impeding factors consider limitations due to economy/capacity of the owners to mobilize the repair works? And again, these are, I know, very specific questions, whereas you were trying to discuss like a general framework. So I think if you were not familiar with the answer, that's perfectly okay with this specific detail.
Yeah, well, I think that the whole issue of impeding factors, that could again be a research project in and of its own. The impeding factors that were used in the study that I showed, those were ones that came out of this methodology called READY, which was developed by folks at Arup. And the impeding factors there were largely based on judgments of panels of a number of experts who gave opinions on that. I think there's certainly more work that can be done to kind of make those more scientifically based, that is based on data and observations.
Okay. I think we are going to switch to our next speaker. Greg, thank you very much. We really appreciate you joining us today. Great presentation. And I look forward to it.
Well, thank you, Sharif. Okay. And thanks everybody for participating and for the questions.